So this is section 3.9, antiderivatives. So we have spent so much time in this class doing derivatives that now we are going to talk about the antiderivative. And in a lot of ways, this is kind of the idea of the opposite of the derivative. You're thinking about functions where the original function is the thing that if you take the derivative, that's what you have. So the formal definition, a function f is called an antiderivative of this little f on some interval if the derivative of f prime of x is this little x for f of x for every x in I. So we're going to take a look at some like basic examples and then to get to kind of a bigger meaning. So for which function is f prime of x equals to 2x? So the idea here is you're thinking about what function, if you take the derivative, do you get 2x? And a lot of you will say, oh, I know that answer. I've done it a million times. It is x squared. And you are correct. But then we're asked the question, but is there only one option? Is there only one function for which the derivative is 2x? Well, the answer is no. And that's because although an x squared is definitely required to get 2x, we want to remember that there is something that you can take the derivative of and get 0. And a lot of you know that that is a constant. Point being, if I were to say add 7 to x squared, or say minus something exciting like pi, those are just constants, they're just numbers. And so when we take the derivative of those functions, f of x, both of them give you 2x, as does even just x squared. Pretty basic, that question. But now if I were to ask you, for which function is the derivative x over the square root of 4 plus x squared, you might think, that's really a lot more complicated than what I just did. And you'd be right, this is a lot more of a complicated function. But it does have an antiderivative, and that antiderivative is the square root of 4 plus x squared. So if you think about it, that's 4 plus x squared to the 1/2. If you were to use the chain rule, bring down the 1/2, you have the same thing inside, it's now to the negative 1/2, and then you take the derivative of the inside and simplify, you would get what you see there. But as I just said, it would be a very hard thing to just guess. But along the same vein here, there is not only one option, because you could have every single time the square root of 4 plus x squared, which is required to get what you have there. But each one of these, each one could have started in a slightly different way because they could all have, as we said before, a constant with them. So this could have had, plus 2/3 or a minus the square root of 10. I mean, any of these things are possible. Even something as basic as plus 1. All of those things, when you take that derivative, are still going to give you this thing we have right here. But that does mean, something a little bit different for us than when we took derivatives. So what you're going to be seeing on the screen here, this is actually on my second monitor, is Desmos. And what I want you to see is that you are seeing the square root of 4 plus x squared with different constants at the end, the different constants that we found as the examples for the antiderivative. And really importantly to see is that every time we have this antiderivative, we have a different constant, and we even have the general form here with the c being 0. But I want you to notice the graphs of each of these. It doesn't really matter which one is which. I just really want you to focus on the fact that all of them have the same shape. The only difference, as you can see in this case, is that the c is different, which of course creates a different y-intercept. And that if you were to choose any point on any of these graphs, so x being 1 or x being 5, you're going to find the same slope of the tangent line because the derivatives of all of these functions are exactly the same. They are that derivative that we saw when we were finding this as the antiderivative. And so that's what's the most important thing to understand about that idea of the general antiderivative versus these more specific antiderivatives with a different c, is that the derivative is all the same, and you're seeing that graphically right now. And it doesn't matter what that c is, that's the only difference that you're going to have. But the slopes of the tangent lines at any point are still always equal for any of those functions that you see on the left-hand side. So when we think about, and I'm still going to stick with that function, when we think about this big f of x equaling the square root of 4 plus x squared, when we just add a c, and this is very common, adding a c being a constant, that's the antiderivative of that thing that we were looking at before. And what we want to understand is that, let me do the theorem first here. If you have big F and big G, if they are both antiderivatives of this little f on some interval, then understand that the only difference between any two antiderivatives is some constant. And we just saw that. So the only difference between all of these possible antiderivatives is that 2/3, the minus root 10, the positive 1, it's just a constant. So we call this type of antiderivative here the most general antiderivative, and that's because c can be anything. It is a constant, and depending on what it is, obviously it changes what that function is. However, the derivative is always the same. It is always what we have up here for that function right there. So what I want you to do now, if you can, is pause and think about these three examples here. Find the most general antiderivative of each of the following functions. So think about what function would you have to start with so that its derivative gives you x to the 4th, or cosine x, or x to the negative 4. So go ahead and try those, and then when you come back, we'll find out if you're right. So for the first one, the idea would be you have x to the 4th. You'd want to start out with one more than that in the exponent, x to the 5th. And you'd also want to be thinking about the fact that since the derivative, that's what we're looking at here, the idea of the f of x being like a derivative here, you'd want to have a 1 there in your derivative. But we know that if we take the derivative of this big f of x, we're going to have 5x to the 4th. So we need to kind of do something that gets rid of that 5 when the derivative is taken. And so we can see that 5 times 1/5 would give us 1. So if you take the derivative of big f of x, you're going to have 5 times 1/5, which is 1, times x, minusing 1 from the exponent gives you x to the 4th. We don't want to forget plus c. For the second one here, we know that sine and cosine have a relationship in terms of the derivatives. So we want to think about what function we would need where the derivative is cosine x. And that's pretty straightforward. It's just sine x. We know that the derivative of sine x is cosine x, so we have that. But we don't want to forget the plus c. For the last one, we want to follow the same pattern we did on the first one. This is just an exponent that happens to be negative. But notice we added 1 to the 4 to get 5 on the first example. So if we add 1 to a negative 4, we're going to get negative 3, because we know if we take the derivative of what we have now, we'd end up with a negative 4 in the exponent. But if I take the derivative of what I have now, I also have a negative 1/3, a negative 3 in the front if I take the derivative. So in order to counteract that, I need to have a negative 1/3, because now if I take the derivative, negative 1/3 times negative 3 is going to give me a positive 1, which is what I have right here. And then I don't want to forget my plus c. I had an instructor when I was in grad school that did workshops for students at UC Davis that were taking calculus. And what he used to tell them to remember the plus c was, he said, you know, when you're doing an exam and you've taken some antiderivatives and you get some right answers and you're feeling really good, you should think in your head, yes. But instead of saying it in English, say it in Spanish. And if you know, of course, in Spanish, yes is sí. So as you take your antiderivatives at the end, you look at it and you go, sí. And then that should remind you that you need to add a plus c at the end of all your antiderivatives so that you don't forget that that is the most general antiderivative, because it's only a general antiderivative if it has the plus c. So that's how to remember c. All right, so now in terms of a more basic, general antiderivatives, we're going to start off with just x to the n. And to find x to the n, the most general antiderivative, this is what we were just looking at. We added 1 to the exponent, and then notice from these past the two examples A and C on the last page, we divided by that, 1 over n plus 1. So you're adding 1 to the exponent, dividing by that thing. This can also be written as x to the n plus 1 over n plus 1. You'll see it written like that. They mean the same thing, so just up to you how you want to write it. We have our cosine. We've already seen that. Antiderivative is sine x. And then I'm going to add my plus c. I realize I kind of did something by giving you two options there, but I'll add plus c to both. Also sine x. So we want to remember, if we were to take the derivative of cosine x, we're actually going to get a negative sine x. But if we just want the antiderivative of sine x, we're going to need to have a negative there. Because if I take the derivative of what you see there, I'm going to have derivative of cosine is negative sine, but a negative sine is a positive sine. Don't forget as well, another comment is our, I'm doing it backwards. I might have spoiled the surprise. So we also want to think about secant squared. That's another one to just remember. And that is, of course, tan x plus c. So obviously, because there's that relationship there, students should know, okay, the derivative of tan is secant squared x. So the antiderivative of secant squared x is going to be tan x, and just kind of keep that in your mind. Also think about if you have two functions added together. So I'll do slightly different notation here. But say you have two functions added together, then you can just take the antiderivative of each piece. So you're going to have f of x plus g of x and then plus c. Very common, right? It's the same with derivatives as well, that you can take the derivative of each piece, you can take the antiderivative of each piece. And similarly as well, if you have a constant, so this is not the same constant as c, but it's just a constant, you can take the antiderivative of your function and multiply it again by k. Those are the same k's. I hope I didn't make you think that that was like a capital K. They're both just k. Just some constant that can be added to your antiderivative. And then, again, your plus c. Don't forget it. Don't forget it. All right, let's take a look at a few examples, and then we'll stop before applications and do that in part 2. The most general antiderivatives are found by just using these rules that we just came up with. But similar to when you take derivatives and you have things like the product rule and the quotient rule, you can't just take an antiderivative unless you have things of the correct form that you can use these rules that we have. So we have f of x equaling this piece right here plus this piece. So we can take the antiderivative of each piece separately. However, don't forget that you can't just take the antiderivative of the top and then the antiderivative of the bottom using that kind of power rule that we just did for antiderivatives. You need to rewrite it first. So we want to divide each piece by x. So thinking about dividing by each piece by x, we will have x squared plus x plus 1, and then plus our 2 sine x. Okay, so rewriting can be very important, just like it is with derivatives. It's also important with antiderivatives, so definitely rewrite it. Now we can take the antiderivative of each of those pieces. So we'll have 1/3 x cubed. So I'm adding 1 to the exponent, dividing by that. For the second term, don't forget that there's an x here with a power of 1 on it. So if we add that, if we add 1 to 1, we get 2. And then if we divide that by that, we get a 1/2. And the antiderivative of just 1, you can think of it like this if you want, that we're basically adding 1 to an exponent of 0, which just gives us an exponent of 1, and then dividing 1 by 1 is still just 1. So it makes sense when you think about it. The derivative of x is just 1. And then we want the antiderivative of 2 sine x. So remember, I can keep that 2 just hanging out and take the antiderivative of sine x, which we have talked about. And we know that that's going to be a negative cosine x. So I'll put a minus here and then a cosine x. And then we don't want to forget that plus c. So there is our general antiderivative of that function, little f of x. Now we're going to do an example of finding a function if we have the second derivative. So we're going to need to take 2 antiderivatives. And these are considered, what we're being given here is initial conditions. That's what these are called, initial conditions. And what they are simply values that allow us to find those constants. So that constant c. And if we have to find 2 antiderivatives, I'm actually going to have a constant also that's called d. And without those initial conditions, all you can do is find the most general antiderivative. But with initial conditions, you can get the very specific antiderivative. And that's what we're going to do now. So we have f double prime. So the first thing we'd want to do is maybe just remember that the square root of x is x to the 1/2. That'll help us. So I'm going to take the first antiderivative. And we've seen 2x already today, so we know that that's x squared. And when we take the antiderivative of x to the 1/2, we're going to add 1 to the exponent, which will give us x to the 3/2. And then we're going to divide by 3/2. So you want to remember that dividing by a fraction is the same as multiplying by its reciprocal. And so that will give us 2/3. And then we have our plus c. But we are not quite where we need to be because we need to find the c. So to find c, we're going to use this f prime of 1 equaling 1. So what that means is when we plug 1 into this first derivative, we should be getting 1 back. And that's what allows us to find c. So this tells me that 1 should equal 1 squared plus 2/3 times 1 to the 3/2 plus c. Again, all I'm doing here is just plugging in 1 to what I just found and knowing that that has to equal 1. So this is going to give us basically 1 equals 1 plus 2/3 plus c, because 1 to the 3/2 is just 1. And the 1's are going to simplify. I'm going to bring the 2/3 to the other side and I get a negative 2/3. So this tells us that that first derivative equals x squared plus 2/3 x to the 3/2 plus c. Ooh, why did I do that? I know that it's negative 2/3 now, so that's what I need to write. I was just taking it from the top. Minus 2/3. So this is our full on, this is the first derivative. This is not a general antiderivative, this is specific. So now that we have that, now we can find our original function. So now let's find the original function. So now we're taking the antiderivative of the first derivative. So down at the bottom here, we're taking the antiderivative of this. So we have x squared. We've seen that today, 1/3 x cubed. We are now going to add 1 to 3/2. That's going to give us 5/2. The exponent is now 5/2. We have 2/3. We need to divide by 5/2. Dividing by 5/2 is the same as multiplying by the reciprocal, which is 2/5. And multiplying those together gives us the new term in the front here, 4/15. There we go. Okay, so our coefficient 4/15. And then we have the antiderivative of 2/3, which, as we've already talked about with some other examples, like the one above where we have 1, it's just x, because the derivative of x is 1, and you're left with that coefficient. Then I'm going to have plus d. Yes, I'm going to have plus d because I don't want to put plus c because this is a different constant. Some students may see in different books and stuff C1 and C2. That's fine. The idea is this is a different number, and so I'm not going to use c, but it's the same thing. It's a constant. So now I need to use my second initial condition, which is that when I plug 1 into my original function, I should get 0. So that allows me to right away, to find d, I'm going to plug in 1 and I should get 0. So I'll have 0. So I have 1/3 times 1 cubed plus 4/15 times 1 to the 5 halves minus 2/3 times 1 plus d. Okay, so this is going to give us 1/3 plus 4/15 minus 2/3 plus d. That should equal 0. So we can put those into common denominator fractions to figure out d. Common denominator here is 15. So we will have 5 out of 15 plus 4 out of 15 minus 10 out of 15. So I'm not worrying about the 1 cubed, 1 to the 5 halves, 1. Those are all just 1. But give everything else a common denominator. You see that's 9/15 minus 10/15 is a negative 1/15. So when I bring that to the other side, I'm going to end up with d equals 1/15. And so what that's going to tell me is that my original function, with those initial conditions, very specific here, is 1/3 x cubed plus 4/15 x to the 5 halves minus 2/3 x, almost there, plus 1/15. So that's the original function. If you were to take a derivative and then a second derivative, you're going to end up with what you see right here. That's the whole idea. But this is the very specific original function, not a general one because we found C and D. All right, last one, and then we will do the rest in part 2. So suppose a function has slope x squared plus sine x at each point on its graph. If f of 0 equals 3, find f. You're welcome to go ahead and pause this if you want to try to find the answer. The only thing you would need to know is that if it's telling you that a function has a certain slope, that is, by definition, the derivative. So we're really just being told here that f prime of x equals x squared plus sine x. And then you can find your antiderivative, use your one initial condition, because it's just one derivative here, and find the original. So go ahead and try that if you'd like, and then come back. So we're back. And the original function here, we've already seen this, a lot of this quite a bit today, 1/3 x cubed. We're going to have the antiderivative of sine. We know that that's a negative cosine of x. And then I'm going to put my plus c. I'm going to use my initial condition that when I plug in 0, I should get 3. I'm just plugging in my 0. Of course, that's gone. And cosine of 0 is 1. So that tells me that c equals 4. And so now I can just write my function with that c. So 1/3 x cubed minus cosine x plus 4. And you'll find, of course, if we take the derivative, that we get that x squared plus sine x, but that this function also has the fact, I don't know, that f of 0 equals 3.